All right. Hello, everyone. I'm Henry Pfister, and I'm part of the Duke Quantum Center. And it's my job to introduce the speakers for the next session. So first, we're going to have Greeshma Oruganti, who's a PhD student in Chris Yarzinski's group at University of Maryland, and also a student postdoc council member at the University of Maryland. All right, today she's going to present her research on bridging quantum thermodynamics, gauge theories, and quantum simulation.
That's working. Thank you so much for the introduction. Good afternoon. The title of my talk is Bridging Quantum Thermodynamics, Gauge Theories, and Quantum Simulation. It is a pleasure to present the work that I did with my collaborators. The talk is primarily based on the publication as well as the archive preprint now. Isn't working? Move it closer. Okay. Is that better? Okay, I'll try and speak much louder. Okay, awesome. Okay, all I said was that the title of my talk was Bridging Quantum Thermodynamics, Gauge Theories, and Quantum Simulation. I'm a PhD student at the University of Maryland, and this is the work that I did with my collaborators, and you can look up the publication as well as the archive preprint, both of which are available. The three fields, quantum simulation, quantum thermodynamics, and gauge theories, at the face of it, seem unrelated to each other. But I believe that not only are these fields related to each other, they also offer deep insight into one another. Quantum thermodynamics is the extension of the macroscopic laws of thermodynamics we know into the quantum realm. And there's been exciting work done at the intersection of quantum simulation and quantum thermodynamics. Some examples include the thermodynamic cost of error correction and how to cool a qubit using quantum refrigeration, which we'll hear about in a little bit. On the other hand, quantum simulation offers a powerful tool to probe the fundamental particles, fields, and their interactions. We can study non-equilibrium processes such as scattering and string breaking in high-energy physics using quantum simulators. And beyond that, an abelian Z2 lattice gauge theory is nothing but a surface code. And so these two fields of gauge theories and quantum simulation are deeply connected to each other. We believe that our work for the very first time bridges the fields of quantum thermodynamics and lattice gauge theories by demonstrating how to compute thermodynamic quantities for a lattice gauge theory. We discovered a new relationship or a new bridge between quantum thermodynamics and quantum information science that potentially allows us to verify our framework on a quantum simulator. And by the end of this talk, I'd also like to convince you all that our work offers a way to verify quantum simulation experiments. This talk is divided into three parts. In the first part, I'll introduce what strong coupling quantum thermodynamics is and how it's related to quantum information science. In the second part, we'll focus on experimentally realizable quench processes. And for a system that's strongly coupled to a reservoir undergoing such processes, I'll define what work and heat are, and we'll see if they satisfy the second law of thermodynamics, and we know that no process can violate the second law. And finally, in the third part, we'll apply this entire thermodynamic framework to a Z2 1+1 dimensional lattice gauge theory, in which we'll see exciting applications and implications for quantum simulation experiments. Let's begin with the first part. The usual thermodynamic setup includes a system whose Hamiltonian is H sub s, and it's interacting with the reservoir, and reservoir's Hamiltonian is H sub r. The interactions between the system and the reservoir are given by V sub s union r. And so the total Hamiltonian that's governing S union r is given by H sub s union r. It's simply the sum of the system, reservoir, and interaction Hamiltonians. The general state of the system reservoir composite S union r is denoted by rho sub s union r. And to obtain the general state of the system, all we do is trace out the reservoir degrees of freedom from rho sub s union r, and the reduced state of the system is denoted by rho sub s. The equilibrium state of S union r at temperature beta inverse is given by pi sub s union r, and it's simply the Gibbs state under the total Hamiltonian H sub s union r. Z here is the partition function or a normalization factor. To obtain the equilibrium state of the system, we trace out the reservoir degrees of freedom from pi sub s union r to obtain pi sub s. It's important to note that pi sub s is not necessarily always a Gibbs state under H sub s, and to understand why that is the case, let's talk about the differences between weak coupling and strong coupling quantum thermodynamics. The total Hamiltonian is, again, a sum of the system reservoir and the interaction Hamiltonians. In standard thermodynamics, it's a common practice to ignore these interactions or really set them to zero. And in such cases, the states of the system and reservoir are always separable, or they're always in a product state. And so the system's internal energy can simply be defined as an expectation value of H sub s in a given state of the system. And in such cases, the Gibbs state of the system is the thermal equilibrium state, which is pi sub s naught. Free-coupling thermodynamics has been well studied for both classical as well as quantum systems. On the other hand, when these interactions are at least comparable, the expectation value of the interaction term is at least comparable to the expectation value of H sub s, we can no longer ignore these interactions while formulating the thermodynamics of the system. And so in those cases, the internal energy of the system is no longer simply the expectation value of H sub s, because this doesn't take into account the interactions or the effects of the interactions on the internal energy of the system. And so the equilibrium state of the system, pi sub s, is no longer the Gibbs state under H sub s, because again, this doesn't account for the interactions. Strong coupling thermodynamics has been well studied for classical systems, and in our work, we aim to extend this to quantum systems. I said that the thermal equilibrium state of the system, pi sub s, is not a Gibbs state under Hs, but we can write it to look like a Gibbs state under this new operator Hs star. Hs star is the Hamiltonian of mean force, and it's defined as minus 1 over beta times the log of the ratio you see on the screen. Essentially, this is a Hamiltonian-like operator that acts on the system and that captures the effects of the interaction on the equilibrium state of the system. Because this operator Hs star doubles as an effective Hamiltonian on the system's degrees of freedom, it's natural to define the internal energy of the system, U sub s, as an expectation value of this operator Hs star in a given state rho sub s. This definition of internal energy is defined for both equilibrium as well as non-equilibrium states of the system. And what's cool about this definition of internal energy is that you need to only measure it on the system's degrees of freedom with no regard to what's going on in your reservoir. Using this operator, the Hamiltonian of mean force, we can define other thermodynamic quantities, such as the free energy, F sub s, which is defined as minus 1 over beta times log of the partition function Zs star. The partition function depends on the Hamiltonian of mean force. When the system is in equilibrium, the free energy F sub s is related to the internal energy as U sub s minus the inverse temperature beta times the entropy S. And so if you do some algebra, we end up with the equilibrium entropy of the system, which turns out to be the von Neumann entropy in a given state, in a given equilibrium state of the system. So now that we have the definitions for the key thermodynamic quantities, internal energy, free energy, and entropy, the question is, can we measure these quantities on a quantum simulator? All the quantities that I defined so far use this operator, the Hamiltonian of mean force, and this contains logs and partial traces, and we potentially can't expect to measure this operator on a quantum simulator. But we can measure a related quantity known as the entanglement Hamiltonian, and it's denoted by H sub ENT, and it's defined as the negative log of the reduced density matrix rho sub s. This object, the entanglement Hamiltonian, has been widely studied in the literature on condensed matter as well as quantum information science. It has been used to characterize topological order, as a tool to study thermalization and gauge theories, and is widely used in quantum state tomography. We discovered that this entanglement Hamiltonian is related to the Hamiltonian of mean force when the system is in equilibrium, where the Hamiltonian of mean force, Hs star, equals 1 over beta times the entanglement Hamiltonian plus the free energy of the system, F sub s. So instead of measuring the Hamiltonian of mean force and all the thermodynamic quantities related to that, we can instead measure the right-hand side of the last equation, which would simply mean measuring the entanglement Hamiltonian and the free energy of the system, F sub s. But most of the times, it's not the absolute value of the free energy we're interested in, rather the changes in the free energy. And so let's talk about some processes that will lead us to measure the change in free energy. In the second part, I'll focus on sudden quench processes in which the Hamiltonian of the system is changed, or rather the total Hamiltonian is changed abruptly. And when the system is undergoing such processes, we can define work and heat. And spoiler alert, the entire aim of the section is to define these quantities, work and heat, in a way that satisfy both the first and the second laws of thermodynamics. We begin our process in a global equilibrium state pi sub s union Ri under the initial Hamiltonian H s union Ri. The initial equilibrium state of this system is simply obtained by tracing out the reservoir degrees of freedom to get pi sub si. At time t equals 0, we abruptly change the total Hamiltonian from H s union Ri to a final Hamiltonian of H s union Rf. So at a time slightly after 0, we have this new Hamiltonian, but the state of the system remains the same due to sudden approximation. And from 0 plus all the way to the final time t sub f, we let the system and the reservoir evolve under this final constant Hamiltonian until they reach their final states, where the final state of the system here is denoted by rho sub s f. There are two stages in this process. The first are around t equals 0, where the Hamiltonian is changing, but the state of the system remains the same. And so the change in internal energy due to the change in the Hamiltonian is what we refer to as work. And in the second stage, from 0 plus all the way to the final time, the Hamiltonian remains constant, but the internal energy of the system is changing solely due to the change in the state of the system. And so this change in internal energy is what we refer to as heat Q. And by construction, the first law of thermodynamics is satisfied, where the total change in internal energy, delta U sub s, is equal to the sum of work and heat. For this entire process, we can also define the change in free energy, delta F sub s, and we analytically prove that work done in this process, W, is always greater than or equal to delta F sub s, which is the statement of the second law of thermodynamics. Now, if we were to end up in a final equilibrium state, then we can also restate the second law in terms of heat and change in entropy, as Q is less than or equal to the change in entropy delta S times the inverse temperature beta inverse, times the temperature actually. And so this proves the statement of the second law of thermodynamics, and we have work and heat that both obey the first and the second law of thermodynamics. And so the next question is, can we measure these quantities, work and heat, in a quantum simulator? For an equilibrium state of the system, we know that the entanglement Hamiltonian and the Hamiltonian of mean force are related via the first simple equation. And from quench processes, we know that work is simply the change in the expectation value of the Hamiltonian of mean force before and after the quench. The state remains the same due to sudden approximation. On substituting the first relation into the definition of work, we obtain work in terms of the change in the entanglement Hamiltonian, or the change in the expectation value of the entanglement Hamiltonian, plus the change in free energy delta F sub s. To measure work, we can measure the right-hand side of the third equation. So you would measure the change in expectation value of entanglement Hamiltonian and change in free energy delta F sub s. And often measuring delta F sub s is very expensive because we would probably have a large reservoir which has many degrees of freedom, or simply the reservoir's degrees of freedom are inaccessible in experiments. So instead, we could measure W minus delta F sub s, which is known as dissipated work, and this quantity can simply be written in terms of the difference in the expectation values of the entanglement Hamiltonian, which we can measure experimentally. And so to verify the second law, all we need to do is measure dissipated work on a quantum simulator and make sure that it stays greater than or equal to 0. And this connection between quantum thermodynamics and quantum information science allows us to potentially verify our framework on a quantum simulator. With this, we come to the third part of the talk, in which I'll apply the thermodynamic framework to a lattice gauge theory, and we'll look at some numerical results for this. First, I'll begin with explaining what gauge theories are, and then we'll look at the numerical results and the implications for quantum simulation experiments. The best description we have of our fundamental particles, fields, and their interactions involves quantum chromodynamics, or QCD, and lattice gauge theories are obtained by discretizing space and time in these theories. And so lattice gauge theories essentially allow us to study QCD non-perturbatively. Hamiltonian formulations of lattice gauge theories are best suited for quantum simulation experiments, but these formulations are inherently redundant. And so to remove these redundancies, one imposes local constraints called Gauss's laws, and these are explicitly implemented in Hamiltonian formulations. From electrodynamics, we know that the Gauss law states that the electric field flux coming out of a surface must be proportional to the charge enclosed by the surface. Using this and boundary conditions, we fix the gauge in electrodynamics. We do exactly the same in gauge theories, where we use these Gauss's laws to fix the gauge in lattice gauge theories. This can be visualized in terms of the Hilbert space as follows, where the entire Hilbert space is split into two subspaces, and all the states that satisfy the Gauss law constraints are fully contained in this physical subspace. And so all our dynamics must be restricted to this physical subspace. To give a more concrete intuition for what Gauss's laws are, how they're implemented in these Hamiltonian formulations, consider this simple spin model that contains two spin-half particles. One belongs to the system, labeled S, and the other belongs to the reservoir, R. Both of them are governed by the respective Hamiltonians, which are proportional to the respective Pauli Z operators. The two spins interact via the interaction Hamiltonian V sub S union R. It contains two terms. The first term is K times the identity minus the product of the sigma Z operators. And the second term is proportional to the product of the sigma X operators, the system and the reservoir. And the total Hamiltonian governing these two spins is simply a sum of HS, HR, and V sub S union R. We know that the total Hilbert space of these two spins is 4-dimensional, but in the limit that K goes to infinity, the physical Hilbert space essentially has shrunk down to a 2-dimensional up, up, down, down basis. This is exactly how one imposes Gauss's laws in gauge theories, by penalizing transitions to other unwanted states and restricting our dynamics to a physical subspace. A large K also means that the expectation value of this interaction Hamiltonian is at least comparable to the expectation value of H sub S, which means these interactions can no longer be neglected while formulating the thermodynamics of our system of interest. And the simple spin model illustrates why strong coupling quantum thermodynamics is the most appropriate framework to study the thermodynamics of lattice gauge theories. Let's now consider a more realistic example of a lattice gauge theory, which consists of, the system here consists of 6 lattice sites on which spin-half particles exist. The subsystem of interest on which we intend to define thermodynamic quantities is labeled S for system of interest. It contains 4 lattice sites, shown in pink, and there are spin-half particles that exist in all these lattice sites. The rest 2 belong to the reservoir, labeled R. These lattice sites are connected via links on which more spin-half particles live. And the entirety of S union R is governed by a Hamiltonian, a Z2 1+1 dimensional lattice gauge theory that's coupled to spin-half hardcore bosons. The total Hamiltonian is denoted by H sub S union R. It has 4 types of terms. And these 4 types of terms can be separated into HS, HR, and V S union R, which is a form familiar to thermodynamicists. We have a systematic way of separating these 4 terms into HS, HR, and V S union R. I won't go into the details, but you'll see some illustrations as I explain these terms briefly. The first set of terms are the matter hopping terms, which tell us that when a spin-half boson hops from one lattice site to another, the spin on the link flips its sign. The next set of terms are the gauge field terms, which are essentially the electric field terms of the spin-half particles on the links. And then we have the staggered mass terms, which depend on the number of particles at each lattice site due to the sigma plus sigma minus operator. M is the mass of the boson. And the next we have the chemical potential term, which again act on the lattice sites, depend on the number of particles, and mu is the strength of the chemical potential term. We now subject this entire S union R to a chemical potential quench, and the quench happens only in the system's degrees of freedom. So the system Hamiltonian consists of the 4 types of terms: hopping, gauge field, mass, and chemical potential term. In this chemical potential quench, we change the chemical potential term only in the system's degrees of freedom by changing the value of mu from an initial value of 0 to a final value of mu sub f at time t equals 0. For this process, all other terms are kept constant, and we can compute the dissipated work, which we do, and we plot it as a function of the final quench parameter mu sub f. Dissipated work, W minus delta F sub s, always stays above 0, which means that work is always greater than or equal to delta F sub s in this case. And these numerical results verify our analytical proof of the second law of thermodynamics. So to verify that our system essentially obeys the second law of thermodynamics, in this case, the lattice gauge theory in a quantum simulator, it is sufficient to measure dissipated work and make sure that it always stays above 0. But there's something interesting happening on the plot here at a point that I've labeled mu sub fc, where the behavior of the dissipated work curve changes drastically. And to investigate this, we overlaid this graph with that of an autoparameter. The autoparameter here is the chiral condensate. It's denoted by sigma, has an expression that's shown on the screen. And chiral condensate is known to have different values in different chiral phases of the theory. And in this case, the chiral condensate, which is plotted in teal, again, as a function of mu sub f, changes its value from a negative value to a 0 value exactly at the same time the dissipated work changes its behavior. And this tells us that dissipated work qualitatively signals a chiral phase transition in the Z2 gauge theory. Ken earlier today urged us to all work for RC1, and so I'm going to speculate here a little bit more and say that if we were to make sure that a quantum simulator is getting the physics correct, all we need to do is study these phase transitions, which can be detected by measuring these thermodynamic quantities, which are experimentally accessible. And as long as our system essentially obeys the second law, we're good to go. That brings me to the end of my talk. I've motivated why lattice gauge theory should be studied under the language of strong coupling quantum thermodynamics. And for a system that's strongly coupled to a reservoir, I define thermodynamic quantities such as internal energy, free energy, and entropy. When this system undergoes sudden quench processes, I define what work and heat are such that they satisfy the first two laws of thermodynamics. We then applied this entire framework to a Z2 1+1 dimensional lattice gauge theory that's coupled to spin-half hardcore bosons, in which we saw that dissipated work qualitatively signaled a chiral phase transition. And the key point of this talk is this bridge between quantum information science and quantum thermodynamics that potentially allows us to verify our framework on a quantum simulator. Looking forward, we actually would like to measure work and heat for a strongly coupled system, in these cases, a lattice gauge theory and a quantum simulator. And I focused most of this talk on sudden quench processes, but a natural question to ask is, can we extend this for other non-quench processes? So we can study non-equilibrium processes, such as scattering and string breaking for gauge theories, potentially in a quantum simulator again. I'd like to thank my wonderful collaborators, Zora Dawoodi, my advisor, Chris Jarzinski, Nicholas Mueller at the University of New Mexico, Connor Powers and Nicole Younger-Halpern. Connor was the force behind the numerical calculations for gauge theories. I'd also like to acknowledge my funding sources, and thank you all so much for your attention. I'm happy to answer any questions you have.